Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome back. Today, you've brought us some really compelling material about one of the most perplexing discoveries to come out of the James Webb Space Telescope recently.
That's right. It comes from a Carnegie-led team, and it's all focused on one specific exoplanet that is, well, it's really challenging some core assumptions.
And our mission for this deep dive is to get to the heart of that. We want to unpack the data and figure out why a planet that, by all rights, should be a dead, scorched piece of rock seems to have a thick, thriving atmosphere. So the planet we're talking about is called TOI-561b. And just to set the stage, this is a super-Earth. It's rocky, it's ultra-hot, and it's so close to its star that, honestly, the models all predicted it would have been blasted clean of any atmosphere billions of years ago.
And yet it hasn't. The data is.
Yeah.
It's pretty unambiguous.
So this isn't just some small update. We're talking about something that could fundamentally rewrite our understanding of how planets survive in extreme environments.
Exactly. And it's not just about survival. This one observation, it just upends the conventional wisdom about these so-called ultra-short period planets.
Ultra-short period, meaning they orbit their star in... What?
In less than one Earth day. It's an entirely different class of world.
Yeah.
And the context here is just as important. This isn't just any star system. It's ancient. We're looking at a planet that is fundamentally different from anything in our solar system. And it's giving us this incredible window into how planets might have formed in a very different chemical environment, way back in the early days of the universe.
Okay, let's unpack this. I think we have to start with the planet itself, the sheer extremity of its environment.
Absolutely. The conditions are almost unimaginable.
So let's lay out the basic profile. We know it's a rocky planet, a super-Earth. What does that actually mean in terms of its size and mass?
So super-Earth is a category for planets that are more massive than Earth, but significantly less massive than our ice giants like Neptune. In this case, TOI-561b is firmly terrestrial. It has a solid surface, but it's packing about twice the mass of our own planet.
Twice the mass of Earth. That's substantial. But you're right, the mass is only part of the story. The location is... it's the real shocker here.
It really is.
The sources say it orbits its star at 1/40th the distance of Mercury from our sun. 1/40th.
I'm trying to even picture that.
It's hard to visualize. So take Mercury, which is already, right up against the sun, practically skimming its surface from our perspective.
Right.
Now imagine moving it 40 times closer to that furnace. That's the neighborhood TOI-561b lives in.
So a year on this planet, one full orbit, is just 10.56 hours.
Just over 10 hours. It completes an entire trip around its star in less time than a workday on Earth.
That speed is just dizzying. And the radiation, I mean, the amount of energy hitting that surface must be terrifying. Terrifying is a good word for it. Scorching almost feels like an understatement. If you were to calculate the flux of stellar energy bathing this planet, it's just astronomical.
And what does that kind of intensity do to a planet's atmosphere?
Well, it has a couple of immediate and usually devastating implications. First, the gas envelope is exposed to these incredibly powerful solar winds. And these winds are constantly, relentlessly stripping away the lighter elements. Like hydrogen, helium, they're just getting blasted off the top of the atmosphere into space.
So it's like a constant erosion process.
A very aggressive one. And that's just the first problem. The second is the heat itself. The energy input is so high that the gas molecules get heated up, they move faster and faster, and they can actually achieve escape velocity. They literally boil off the planet over time.
So based on everything we thought we knew, if this planet ever had an atmosphere, it should be long gone.
It should be a distant memory. For a small, hot, rocky planet like this, any primordial atmosphere it formed with should have been lost within, say, the first few 100 million years of its life.
And this star system is much, much older than that.
Much older. We're talking about a system that's around 10 billion years old. After that amount of time, any atmospheric remnant should be, well, negligible, a wisp of vapor at most. But that is not what the JWST is telling us.
And there's another complication. The proximity to the star means this planet is almost certainly tidally locked. Can you explain what that means for a planet, especially one this close to its star?
Sure. Tidal locking is what happens when the gravitational pull of a large body like a star forces a smaller orbiting body, the planet, to synchronize its rotation with its orbit.
Like our moon is with Earth, we only ever see one side.
Exactly the same principle. Since TOI-561b's orbit is 10.56 hours, its rotational period, the length of its day, is also 10.56 hours. The practical upshot is that one hemisphere is locked in perpetual, unending daylight, while the other is trapped in eternal darkness.
So one side is constantly being cooked and the other is frozen.
If it were a bare, airless rock, yes. The consequences would be an unimaginable temperature gradient. The day side would be superheated to, thousands of degrees, easily hot enough to vaporize rock into a magma ocean.
A literal ocean of lava.
A permanent one. Meanwhile, the night side, facing the cold of deep space, would radiate its heat away and cool down rapidly. It would likely be solid rock, perhaps even frozen solid, depending on the composition.
And that difference in temperature, from molten to solid rock, that must create some incredible physical stress on the planet.
Immense thermal stress. It would likely lead to huge cracks, faults, and rampant volcanism as the planet tries to sort of equalize that energy. It really should be a world defined by thermal catastrophe.
So this is a world that should have no air, should be half molten and half frozen, and basically be tearing itself apart. But the evidence suggests it's resilient, and the key to this whole puzzle seems to lie with its parent star.
It does. It all comes back to the star.
Our sources say the star, TOI-561, is a bit smaller and cooler than our sun, but it's ancient, twice the age of the sun. And critically, it's described as iron-poor and located in the thick disk of the Milky Way. Let's unpack that, because that sounds like a lot of astronomical jargon.
Right.
What does that combination of traits actually tell us?
Okay, so the location is hugely important. The Milky Way galaxy isn't just a uniform blob. It has structure. There's a thin disk, which is where we live, where our sun is. It's dense. It's where most of the star formation is happening now.
And then there's the thick disk.
Right. The thick disk is an older, more diffuse, sort of puckier structure that surrounds the thin disk. Stars in the thick disk are ancient. They formed very early in the galaxy's history, probably between 8 and 10 billion years ago. So finding the star there is what gives us that incredible age estimate.
So it's like finding a fossil from the galaxy's childhood.
A perfect analogy. And a key characteristic of these fossil stars is that they are metal poor. Now, we have to be clear about what astronomers mean by metals.
It's not just iron and gold, right?
Right. To an astronomer, a metal is any element on the periodic table that isn't hydrogen or helium.
Ah, okay.
The early universe was made of almost nothing but hydrogen and helium. It took generations of massive stars living fast and dying young, exploding as supernovae, to forge all the heavier elements and then seed the galaxy with them. Carbon, oxygen, silicon, iron, all of that is metal.
So an iron-poor star means it was born from a cloud of gas that just hadn't been enriched with those heavier elements yet. The galaxy wasn't fully seasoned, I guess.
Exactly. The protoplanetary disk of gas and dust that TOI-561b formed from was fundamentally deficient in those heavier elements compared to the one that our own solar system formed from about 4.5 billion years ago.
And that has to have a direct impact on the kind of planet that can form.
A huge impact. It gives us a major clue about the planet's internal structure. But more importantly, it makes the fact that it has a sustained, volatile, rich atmosphere even more bizarre.
Why is that?
Because the very building blocks for a complex atmosphere, and even the planet itself, were just scarcer back then. So the fact that this small, ancient, and highly irradiated world not only formed, but held on to its atmosphere, well, it runs contrary to basically every model of planetary survival we have.
So we have a theoretical model that's screaming barren, scorched rock.
Screaming it, yes.
But the scientists weren't just relying on theory. They had an early clue, a piece of circumstantial evidence that something was off. And it came down to a pretty basic measurement, the planet's density.
Right, the mass to volume ratio is the first red flag.
This density calculation really became the central puzzle, the thing that kicked off this whole intensive observation campaign with the JWST. When they first measured TOI-561b, they found it had a really low bulk density. Now, the sources are clear to point out it's not one of those super puff or cotton candy planets, which are almost entirely gas.
No, it's definitely a rocky world. But for a super-Earth with twice the mass of our planet, it was. It was lighter than it should have been. The numbers just didn't quite line up with an Earth-like composition.
And that discrepancy, that low density, immediately presented two competing hypotheses.
Right, and the team had to figure out which one was correct. because they lead to radically different conclusions about the planet.
Let's talk about the first one, Hypothesis 1.
So Hypothesis 1 goes right back to the planet's heritage, what we were just discussing. The star system is ancient and iron poor. So it stands to reason that the planet itself must reflect that.
So its composition is just different from Earth's.
Exactly. The lower density could be explained by a more, you could say, exotic interior. Perhaps it has a much smaller iron core proportionally than Earth does. And maybe its mantle, the rocky layer, is made of lower density minerals things formed from the lighter elements that were more common in that ancient protoplanetary disk.
So that's the geological explanation. The ingredients were just naturally lighter from the start.
Precisely. It's a very neat and tidy explanation. It connects the formation context, the thick disk, the iron poor star, directly to the measurement they made. It's elegant.
But it wasn't the only possibility. And the second hypothesis is the one that really brought the JWST into the picture.
Yes. Hypothesis 2 proposed that the low density wasn't due to the planet's core composition at all. It suggested it was an observational artifact.
An artifact caused by what?
Caused by something hiding in plain sight. A surprisingly thick atmosphere.
Ah, okay. How does an atmosphere make a planet seem less dense?
Well, think about how we measure the size of these distant planets. We use the transit method. We watch it pass in front of its star and measure how much starlight it blocks.
Right. The bigger the planet, the bigger the dip in light.
Exactly. But if a planet has a thick, opaque atmosphere, what you're actually measuring is the top of that gaseous envelope, not the surface of the solid rock core. The atmosphere makes the planet appear larger in radius than it actually is.
So you've got this inflated size measurement.
You've got an inflated radius, but you're using the planet's true mass, which we can measure through its gravitational tug on the star. And when you calculate density mass divided by volume, a larger volume gives you a much lower density.
So the low density itself was the first major hint that this planet was wrapped in a substantial blanket of gas.
It was the strongest initial hint, and it was a direct challenge to all the models that said it couldn't be there.
So the mission was set. Figure out which it was. An exotic, iron-poor interior or a surprisingly stubborn atmosphere. How did the team use JWST to solve this? It seems incredibly difficult to isolate the light from a tiny planet right next to its blazing star.
It's an immense technical challenge, and this is really where the sheer power of the James Webb Space Telescope shines. They used an instrument called the Near-Infrared Spectrograph, or NR-SPEC.
NR-SPEC, okay.
And their entire method hinged on a very long, very painstaking observation. They stared at the system for over 37 hours straight, focusing on a specific event called the secondary eclipse.
The secondary eclipse, that's not the transit, when the planet goes in front.
That's when the planet goes behind the star from our point of view.
Okay, so what does that tell you?
It tells you exactly how much light the planet itself is giving off. Think about it. Just before the eclipse, our telescope is receiving light from the star, plus the light radiating from the planet's scorching hot day side.
Right, a combined signal.
Then, for a short period, the planet is hidden behind the star. During that time, we only get the starlight. All we have to do is subtract the star-only light from the star plus planet light.
And what's left over is the light coming only from the planet's day side.
Precisely. You can isolate the planet's thermal spectrum, its heat signature.
That sounds, that's like trying to measure the light from a single candle flame sitting right next to a giant searchlight.
That's a very good way to put it. You are trying to isolate a tiny whisper of heat energy from a background source that is thousands or even millions of times brighter.
How can an instrument even do that with any accuracy?
It requires incredible stability and sensitivity. NIR-SPEC is specifically optimized to look at near-infrared light, and that's exactly the wavelength where a super hot surface like the day side of TOI-561b would be radiating most of its energy.
So it's looking in the perfect part of the spectrum.
It is, and by observing continuously for almost 4 full orbits of the planet, they weren't just taking a single snapshot. They were accumulating data points over and over again, which allows them to build up the signal and average out the noise. They're not looking for visible light reflecting off the planet. They're measuring its thermal glow, the infrared heat, which is a much more direct way to measure its temperature.
A fascinating look at how these observatories actually work. But okay, let's get to the results. What did that meticulous measurement show? Here's where it gets really interesting. What was the number?
The proof was in the numbers, absolutely. And it came down to a massive discrepancy between what the temperature should have been and what they actually observed.
Okay, so what was the prediction? If TOI-561b was just a bare, airless rock.
The thermal models, Assuming it's a perfect black body just absorbing and re-radiating all that stellar energy, predicting a dayside temperature approaching a staggering 4,900 degrees Fahrenheit.
4,900 degrees.
Or about 2,700 degrees Celsius.
I can't even comprehend that. That's far hotter than the melting point of most rocks. You'd have that magma ocean we talked about.
Guaranteed. It's hot enough to melt and boil steel almost instantly. That was a baseline prediction for a dead, airless world.
So, what did JWST actually see?
The NIR spec data revealed that the dayside temperature was significantly cooler.
How much cooler?
The measurement came in closer to 3,200 degrees Fahrenheit, or about 1,800 Celsius.
Wait, a drop of 1,700 degrees Fahrenheit.
Yes, a massive, massive difference. It's more than 900 degrees Celsius cooler than it should be. There's simply no way for a bare rock to be that cool under that much radiation.
So something has to be getting in the way. Something has to be distributing that heat.
Exactly. That significant cooling effect absolutely must be caused by something substantial. And the only plausible candidate is a thick atmosphere that's actively regulating the planet's temperature.
So it's not just that an atmosphere is there, it's that it's actively working. It's a dynamic system.
It has to be. A simple thin layer of gas wouldn't be enough. You need complex processes to explain that level of cooling.
What about other explanations? Could something else be moving the heat around? What if the magma ocean itself was circulating, carrying heat to the night side?
That's a great question, and the team considered it. A magma ocean could certainly circulate some heat, but without an atmosphere to trap that heat and move it efficiently, the night side would still likely cool down so much that the rock would solidify.
Ah, so you'd have a solid barrier on the night side, which would limit how much heat could flow from the day side.
It would limit the flow, yes. The circulation would be inefficient. You also might get a very thin atmosphere of vaporized rock silicate vapor, but again, a thin layer like that just doesn't provide the kind of global cooling effect that was observed. It can't explain a 1,700-degree temperature drop.
So those simpler explanations just don't fit the data.
They don't. As the researcher said, we really need a thick, volatile-rich atmosphere to explain all the observations.
Volatile-rich, meaning gas is light.
Yeah.
What are we talking about here?
We're talking about things that are gases at lower temperatures than rock. Water vapor, carbon dioxide, maybe even oxygen or methane, though that's less likely at these temperatures. Volatiles, the stuff atmospheres are made of.
And this thick, volatile-rich atmosphere would have several ways of cooling that dayside down.
That's right. The models suggest at least 3 key cooling mechanisms are probably at play here.
Okay, what's the first one?
The first, and maybe the most intuitive, is wind. Really, really strong winds.
Winds on a world that hot with a magma ocean.
Exactly. The extreme temperature difference between the super hot day side and the cooler night side would drive incredibly powerful atmospheric circulation. These winds would pick up heat from the scorching day side and physically transport it over to the night side.
So it's like a planetary scale air conditioner. It's just moving the heat around the globe, preventing it from building up in one spot.
That's the perfect way to think about it. It lowers the maximum temperature on the day side by spreading the energy out more evenly.
Okay, so that's one. What's the second cooling effect?
The second is gas absorption. Those volatile gases we mentioned, water, carbon dioxide, things like that, are very good at absorbing near-infrared light.
The very light that JWST is looking for.
The very same. So the hot surface is radiating this infrared light. But before that light can escape into space and reach our telescope, the atmosphere absorbs some of it. From our perspective, the planet just looks dimmer and therefore colder than it actually is at the surface.
So the atmosphere acts like a filter, blocking some of the heat signature.
It does. It's another piece of the puzzle that contributes to that lower observed temperature.
And the third mechanism?
The third possibility is clouds.
Clouds on a lava world. What would they even be made of?
Well, not water, obviously, but you could potentially have clouds made of silicate minerals, tiny droplets of vaporized rock that condense at higher, cooler altitudes.
And if those clouds are bright?
If they're bright, they would act just like clouds on Earth. They would reflect a significant amount of the incoming starlight back into space before it ever even has a chance to heat the surface. It's another way to cool a whole system down.
So you have this three-pronged effect. Winds moving heat, gas absorbing heat, and clouds reflecting heat. And together, they can account for that 1,700-degree drop.
That's the model that best fits the data we have so far. A very active, very complex atmospheric system.
Which brings us to the biggest question of all. The one that started this whole thing. How can a small planet, this close to its star, in this much radiation, hold on to any atmosphere, let alone a thick and complex one. It should have been gone billions of years ago.
And this is, I think, the most profound part of the discovery. The answer seems to be the concept of equilibrium.
Equilibrium, meaning it's not just holding on to its original atmosphere, but it's being replaced.
It's being constantly replenished. The lead author of one of the studies introduced this fantastic analogy. They said this planet is likely much, much more volatile rich than Earth. They described it as, and this is a quote, really like a wet lava ball.
A wet lava ball. That is an incredible image. What does that mean?
It means the planet's interior, its magma, is saturated with dissolved gases, the same volatiles that make up the atmosphere. And what's happening is a dynamic cycle.
A cycle. Okay.
So yes, gases at the top of the atmosphere are constantly escaping into space. The star is still blasting them away. That part of the old model is still true.
Yeah.
But at the same time, the intense heat is causing gases to constantly come out of the magma ocean to feed the atmosphere from below. It's called outgassing.
So it's losing atmosphere, but it's also making new atmosphere at the same time.
Precisely. And it's even more complex. The thinking is that the magma ocean is also sucking some gases back into the planet's interior. So you have this three-way exchange: gas escaping to space, gas outgassing from the magma, and gas being reabsorbed by the magma.
A constant recycling process.
A dynamic equilibrium. The atmosphere isn't a static leftover from the planet's formation. It's a feature that is being actively maintained, recycled, and replenished by the planet's own geology, moment by moment. That is how it survives.
That completely changes the picture. It's not a question of how long a planet can keep its atmosphere, but whether it has the right internal ingredients to continuously make one.
You've hit it exactly. And that's where the planet's origins become so important again.
Right. Let's connect the dots back to that ancient iron-poor star. How does the planet's formation in the early universe relate to it being this wet lava ball?
Well, remember, that star formed when the universe was younger and less chemically enriched. The protoplanetary disk was poor in heavy metals, like iron, but it may have been comparatively rich in other things.
Volatiles, water, carbon.
Exactly. It's possible that planets forming in that environment incorporated a much higher fraction of volatile materials into their bulk composition from the very beginning.
Mm-hmm.
The building blocks themselves might have been soggier, for lack of a better word.
So TOI-561b's composition isn't just an oddity. It's likely representative of the kinds of planets that formed when the universe was relatively young.
That's the really exciting implication, and it fits with that initial density puzzle. The low density, the likely smaller iron core, and the less dense mantle. All that makes perfect sense if the planet formed in an environment that was chemically different from our own.
So what does this all mean? Let me see if I can summarize the aha moment here for you.
Go for it.
We found a planet that proves that even under the most hostile, ultra-hot conditions imaginable, if a world forms with enough volatile material packed into its interior, if it's a wet lava ball, it can establish this incredible dynamic equilibrium, a cycle of outgassing and reabsorption that allows it to maintain a thick, protective atmospheric blanket indefinitely.
That's a perfect summary.
And it completely expands the range of possibilities for where atmospheres can survive. We used to look at planets like this and just write them off as cinders.
They were written off.
Yeah.
They were considered the worst possible places to look for atmospheres. And this discovery tells us we were wrong. It suggests there might be a whole class of resilient, geologically active worlds out there that we've been completely ignoring.
It's worth mentioning the scale of this research, too. This wasn't just a quick look.
Oh, not at all. This result is just the first from a huge JWST program, General Observers Program 3860. It involved that very long 37-hour observation we talked about. And the team is still analyzing the full data set.
What are they hoping to find in the rest of that data?
The next big step is to try and map the temperature all the way around the planet. They want to measure the temperature of the night side as it rotates back into view.
And that would tell them how efficient that heat transport really is.
Exactly. It would put real constraints on those wind speed models. And they're also digging deeper into the spectrum of the atmosphere itself. The goal is to try and pinpoint the precise chemical composition. Is it mostly carbon dioxide? Is there water vapor? Knowing the specific gases will tell us even more about the planet's geology and formation.
So there's still a lot more to come from this one world.
We're just scratching the surface.
Let's just recap the absolute key findings then. We have TOI-561b, a scorching super-Earth, orbiting its ancient star every 10.5 hours. A place where we expected to find a bare rock heated to nearly 5,000 degrees Fahrenheit.
The before picture, yes.
Instead, we find a world that is over 1,700 degrees cooler than expected, shielded by a thick atmosphere that it actively maintains through a dynamic equilibrium with a volatile, rich magma ocean below.
The wet lava ball in action.
It's a phenomenal discovery. I like the quote from the lead author, Ioana Teske, that you flagged for us. She said, "What's really exciting is that this new data set is opening up even more questions than it's answering."
And that is always the sign of a truly great discovery in science. It's not about closing the book. It's about realizing the book is much, much larger than you ever thought it was.
So we always like to end by leaving you, the listener, with a final provocative thought, something to mull over. What's the big takeaway here that we should be thinking about?
Well, I think it comes back to the age of this system. This planet and its star formed when the universe was younger, when it was less chemically enriched with the heavy elements we see around us today.
Right, it's a relic from an earlier cosmic era.
It is. So if a world like this, an ancient world born in a metal-poor environment, can not only form with enough volatiles, but can then maintain a complex atmospheric cycle for 10 billion years under the most extreme conditions. What does that imply for all the other older exoplanets out there? Think about the sheer number of planets orbiting ancient stars in the thick disk or in globular clusters that we might have overlooked. How many of them have we dismissed as bare rock candidates, when they might actually be hosting these incredibly resilient dynamic systems?
It suggests there could be a huge hidden population of worlds with atmospheres where we never thought to look.
It forces us to reconsider what makes a world survivable, not for life perhaps, but for its own atmosphere. The universe might be far more capable of creating and sustaining these kinds of worlds than our models ever gave it credit for. And that's something for you to think about as you continue to explore the cosmos.
A fascinating thought to end on. It's a reminder that every new data point can completely change our perspective. Thanks for joining us for this deep dive.